Second speaker is Haisen Zhao from Shandong University, and his talk will be in efficient design and fabrication for complex geometries. Haisen Zhao is a professor at the School of Computer Science and Technology in Shandong University. Actually, he's also my colleague. And his research interest lies in computer graphics and their application for digital fabrication. He completed his PhD at Shandong University under supervision of Professor Baoqian Chen and received master's and bachelor degrees also from Shandong University. And Haisen Zhao was postdoctoral at the University of Washington, working with Professor Adriana from 2019 and 2021. And he was postdoctoral at the Institute of Science and Technology at Austria, as well as ST Austria, working with Professor Bernd Bickel recently for 1 year. And he received the first prize of Shandong Natural Science Award at Shandong Province, in 2020, and the doctoral dissertation award from CCF in 2019. And so let's welcome Haisen Zhao for the talk. And now the floor is yours.
Okay, can you hear me? Okay.
Yes.
I will share my screen. Okay, can you see my slides?
Yes.
Okay.
Yeah, very good.
Cool. Okay, it's my time. Okay. Good evening, everyone. Thanks introduction. Thanks Linda for introduction. It's really my pleasure to give a talk at Asiagraphics. This is my outline of this of today's talk. For the first part, I would like to briefly introduce myself. Even though Linda Liu have introduced myself, I will give some images to show you. My research work mainly focused on computer graphics and the geometry process and their application in digital fabrication. I have just got a professor faculty position at the Shandong University. Indeed, the Shandong University is also where I got my PhD degree, advised by Baoqian Chen. Here I saw some pictures of our campus, our really nice campus, which is located near the sea. So you can see with many very beautiful views. I introduced by Linda. I have two stages of postdoc experiments. One is 2 years postdoc fellowship at the University of Washington, and another one is in Algeria, in STA, advised by Bernd Bickel. Here, I just want to show you some pictures, really nice pictures of the two campuses and my research groups at the two universities. Okay, before talking about my own research, I would like to introduce the background of my work. Take a look at this image. The fabrication process still in our industry still involve significant human effort during the design and the manufacturing process. Given this background, my research, the goal of my research is to improve the production process and reduce the amount of human effort required in the design and the fabrication. So in a bit summary, my main goal is I want to produce many computational tools for the next industry revolution. So what's the key benefit of this direction? Firstly, it is used to answer this problem: what we can make. We need to design products of specific functions, such as interactive structures, multi-material products, or functional textiles. And the second problem we can answer is how we can make it. We need to generate the fabrication plans in a low-cost, efficient, or robust manner. Here is another answer to the same problem of why we want to build such tools to help make sense. This answer is a mathematical formulation from Professor Jim Khan of the CMU. I just read his test. Given that there are instances to be created or design or fabrication, it's always take effort E. Then research of cost R can reduce the E to E prime. Note that in the industry or in our common life, here in the equation, the E can be a really large number. It can be a million or a billion, so it's a really large number. Therefore, even if the E prime is only a bit better than the E, it can still very useful. It means we can save a lot of money or other benefit from this. So I really like this equation to solve why we want to build tools to help make sense. So what problem I have worked on in my research? Okay. All my existing work can be grouped into three subjects. For first one, for first topic, we would like to speed up the product upgradation process by reducing the iteration between the designer and the fabrication engineering. What's the meaning of this problem? I want to talk about more. For fabrication, we always start from a design, and then we would like to optimize the fabrication process for what model to minimize fabrication cost. During this process, this is important because the fabrication is design dependent. However, when we design, creating or modeling a design for its physical behavior, we need to consider or understand the fabrication process, as the fabrication process indeed is define the physical what we can physically realize. So from the picture we can see a cupping relationship between the design and the fabrication. So with the cupping relationship, make the optimization really challenging. We want to explore this challenge problem on the carpentry domain. For example, imagine if we want to fabricate this simple birdhouse, this can be done with many different cutting tools, bandsaw, jigsaw, table saw, or chop saw. Also, packing and cutting in the different ways or different orders can have many different options. All of these decisions or options of cutting tools, or packing or cutting orders will affect the fabrication time, material cost, or even the overall precisions. So this problem is really hard. For this problem, we want to solve it. Our key insight is that we find that both design and the fabrication can be programs. For design, the design process can be expressed as a sequence of geometric operations. It can be a code. And for fabrication plans, it's also a sequence of physical instructions. With this insight, we argue that this insight can help us solve this problem in design for fabrication by draw ideas from programming language domain. In the programming language domain, there is a very famous data structure called the E-graph. The key benefit of E-graph is it can compactly and efficiently represent large-scale equivalent program. What's the meaning of that? Even though you may did not hear about of the E-graph, you may use it in some math software. When you call the simplify, a function called simplify in your in some math software. The idea is that there are two programs are equivalent, and we can go from one program to another one with a sequence of result rules, all called equivalent rules. The space of equivalent is very hard to search, and the eGraph can define a data structure that makes this search tractable. Originally, the eGraph cannot use the full geometry domain directly. We overcome this gap, this problem, by produce the reusability problem and propose a geometric method to populate the eGraph. Here, I'll just ignore some technical details. The key idea is we generate many geometric result rules, geometric equivalent rules to populate the geometry eGraph. Based on the geometry eGraph, we can optimize. We can do a multi-objective optimization. Here I just show some results. We have asked 3 carpenters to design carpentry models use our framework. And here are the results of the design. And the one key benefit of our approach is that our framework can return not only one, but multiple solutions with different trade-offs and allow user to explore what they want, to select what they want. So we also compare with some, compare our method with some skilled carpenters. For most cases, our system can find better solutions than the expert. Okay, for now, we can get some optimal fabrication plan for given design, but we did not consider to optimize the design itself. What if we want to optimize the design itself? Why do we want to optimize the design itself? What's the key? What's the benefit? Here is one example. Here, for this example, consider this model. The following figures show the lowest time cost and the lowest material cost fabrication plans. We can generate design variations by discrete varying the joints of the input design. With the 2 design variations, now we are able to generate a fabrication plan that is 30% faster to the material for fabrication, and the one that can reduce the material cost by 15%. So in this work, we propose a new method that allows user to consider the space of possible design variations when optimized for fabrication plans. Indeed, this problem is a typical multi-level optimization problem, where each carpentry design variation determine a large-scale certain space for fabrication plan. And our key insight to solve this is that equivalent substructures within a single design and across different design variations. Also, based on the eGraph data structures, we propose a new eGraph called a bag of parts eGraph to represent the design and the fabrication in a single certain space. Even we use eGraph, the certain space is still really large. So how do we search? How do we optimize based on the bag of part eGraph? We propose an iterative create extraction algorithm. Also, I'll skip the detail of this algorithm. For results, we have tested our method on this different kind of geometries. As shown, in this example, we can further reduce the fabrication time and the material cost by including some new design variations. This slide shows the fabrication time. More results, we show the number with the percentage. For the material cost, we we compute the material cost by the money, by the dollar number. We can reduce the material cost by including some new design variations. Here are some more results. Okay. For my second subject, we aim to improve fabrication efficiency and the quality, particularly for some complex geometries. However, the fabrication plan for complex geometries always still require some human effort, such as the fixture design and the setup planning process. In this topic, I will talk about 3 projects. For first one, we focused on 2-pass planning for 3D printing. In 3D printing domain, the zigzag is the most popular field patterns. However, zigzag field patterns have 2 key drawbacks. One is discontinuity. The second is there are so many subtrains as shown in this animation. So ideal of 2-pass should be a long and a continuous 2-pass with low curvature. To get such ideal 2-pass, our key in the idea is to include the formula spiral. Here is a formula spiral for square region. Compared to original spiral or single spiral, we can find that its start and end point are all along the region boundary, and the two endpoints can be placed anywhere on the region boundary. With the 2 observations, we can allow to connect it multi-furnace spiral to be a single 2-pass, as shown in this figure. So in this work, we introduced a new 2-pass called connected furnace spiral, which achieve global continuity and form as a long and low curvature 2-pass, as shown in this butterfly. For results, we have tested our method on a set of shapes with different degree of complexities. The connected formula spiral is very suitable for this kind of shapes with honeycomb input shapes with all 2D slicer layers of 3D porous structures produced by our another paper. Imagine that if we use the zigzag 2-pass to fill such shape, there will be many subtrains and many non-continuous 2-pass. Just like 3D printing, we also need to do the 2-pass planning for subtractive manufacturing. Instead of filling 2D layers, we must carve over curved surfaces. So an interesting question is, can we apply connected formula spiral from 2D to 3D to freeform 3D objects? Another difference is that we would like to consider curved surface quality by generating uniform distributed scallop, which the scallop is a residue material that is left by the cutter after carving, just like as shown in this figure. Our basic idea to achieve the uniform distribution scallop is to compute an adaptive scalar field whose ISO line can meet the gap requirement. Here are some results. In this work, we propose a so-called ISO scallop connected formula spiral 2-pass. These 2-pass have global continuity, continuous, and uniform scallop distribution. There are 3 properties. We also test this 2-pass by fabricating a set of real 3D objects, as shown in this short videos. Okay, the final project along this topic is in CNC machining of 3 axes because it's only 3 axes. So it's often not possible to machining a freeform shape from a single direction. We always need to multi directions to finish the machining. In practice, each direction needs one setup for machining, which is a very expensive process. You can see from the video, it's very expensive process. During this topic, during this project, we propose a new geometry property called curvability to describe such volume. Indeed, it's a new geometry property. Indeed, it's just a combine between the visibility and monotonicity. And we have a new formulation for this problem. We gave the first formulation of the problem as a volume decomposition problem to minimize the number of setup directions and the number of curvable volume. Note that the curvable volume, it means we can use a single toolpath to machine this volume. Also, I saw some results. We have compared on the left side, our algorithm produce 3 directions. We compare our method with some expert. We can see we use 3 directions, but the expert have to use 6 directions. We can get better results. This is another comparison. For 3D comparisons, we use a simulation process to compare the current time of the direction provided by expert against ours. In all the cases, our algorithm is much faster. Okay, for a third subject, we aim to design new products with some physical requirement, just as the discussion between Linda and Peng. I will also talk about three papers, 3 topics, 3 projects along this topic. For first work, we have introduced a new method for generating perforated lampshade that can project a continuous grayscale image on a surrounding wall. In order to generate a grayscale image distributed on a surrounding wall, we perforate the lampshade with a set of tubes with varying density of each tube, then varying its radius and tilting angles. Indeed, this work can be seen as a 3D half-toning technique, where the basic elements are not 2D dots, but 3D tiny tubes in a thin lampshade cells, have both radius or rotation respect to the light source. For each tube, the light passes through from it which can generate a footprint on the wall. Also, I saw some results of this project. Here are a set of fabricated spherical lampshade. The left is projected image, so the real photographs of this lampshade. Okay, my second project on this topic is a reverse engineering project. The problem is that given a set of images, can we generate a fabricable geometry models? Our key insight is to present object use the fabrication process itself when we do the reverse engineering. In this work, we use a 2D contour and a 1D thickness to describe each part. Here we saw some results. This image shows some results generated by our results. From this image, our framework can generate the footprint or the blueprint, which can be directly fabricable by the user. Okay, As the final project along this topic, we have been inspired by some powder structure for 3D printing to generate the honeycomb cell structures which can resistant and external stress with minimal material cost. Here we saw some more results of such structures. Okay, my next session, I would like briefly just introduce several fields work along my existing works. Okay, here is I have got 3 very specific directions. The first follow-up of existing work is to continue working on the co-optimization between design and optimization. I would like to introduce continuous parameter for generating design variation, such as length, width, and angle. My previous existing work only consider discrete parameters. It's easy to imagine if we including the continuous parameter, it will extremely enlarge the certain space. How do we solve it? It became very challenging. The second specific topic is to include some physical properties during the fabrication plans. For my project, I have been working on the two-pass planning, but during the two-pass planning, we did not consider the physical problem during the optimization. For this, I want to can we take the physical constraint during the two-pass planning? It's a challenge problem. For the third topic, specific idea is called hybrid manufacturing. You can see I have been working on 3D printing or subtractive manufacturing or molding or many other fabrication process. I also imagine can we combine this different kind of material technique, different fabrication techniques. For this specific idea, there are many commercial 3D printing and CNC machining hybrid manufacturing machine. I know there are many such kind of machine, but this kind of machine can only produce very simple geometries. The key challenge is they need some computational tools to generate the fabrication plan for the complex geometries. So we really want to do these directions. Or I also wanted to do some other hybrid manufacturing between different techniques. Here, so a complex roadmap of this project. In my following projects, I really want to use some data-driven method or some human-in-the-loop method to solve this kind of geometry design or fabrication problems. Okay, my final part is a very short summary. My existing research work, my whole research is try to apply graphics technique to produce computational tools for design and fabrications to solve what we can make or how we can make the two problems. Okay, that's my summary. Thanks for your time and attend my talk. I'm looking forward to the following Q&A sections.
Okay, thank you, Haisen, for this very nice and very informative talk. And again, so we are now open for questions and comments from the audience. So do not hesitate to post your comments or questions in the chat box, no matter what channels you're watching. And so I will start from one or two small questions. So the first one is related to the carpentry work. you have a series of carpentry works that integrates the design and the fabrication.
Yeah.
So according to we have the first talk from Professor Peng Song related to these geometric puzzles. I think there are a lot of common points between these two issues. There's the puzzles and the carpentries. As your carpentry is also, at least it looks like the puzzles. It comes from smart decomposition rules, and you need to also consider the assembly sequence, right? So do you have any like comments whether such puzzle, such like this, like interlocking or some other issues can be further applied to this carpentry?
Yeah, I was thinking, firstly, I want to say for a carpentry domain, it's to belong to a subtractive manufacturing, because the input is a big carpentry board. We cut some pieces, some shapes from the big pieces. So it's subtractive manufacturing. But for the for Peng Song's work, the ensemble, we can say it's more like if we assemble during the assemble process, it's additive manufacturing. It's additive manufacturing. But one so this point is different. One is subtractive, one is additive. But when we working on the carpentry domain, we would like to extend the co-optimization between design and fabrication to other domains, including the additive manufacturing. But this indeed is really challenging. As discussion from you and Peng, in his work, he did not consider counter work. He did not consider multi physical property during the design. Indeed, here it's the co-optimization between design and the fabrication process. For a carpentry, it's became simple because firstly it's 2D. It's 2D. Another is there no the order is not there are no indeed for the carpentry problem. There are no assemble. We did not consider assemble. We just consider the fabrication process. Each part is independent, but we have for the assemble process. Yeah, for sure we need to assemble this part to form a chair, but we did not consider the assemble process in our process. For assemble process, it's order dependent, and for Peng Song's is also order dependent. If we want to consider the design optimization and the fabrication process, also the assemble process, if we want to do the optimization, combine the 3 states. The problem is too challenging. Another difference is for carpentry, for our current method is only can only used for discrete parameter. We did not consider continuous parameter. But for example, for 3D printing, there are many continuous parameters, just as Peng Song's work. But for some example, for some assemble is also discrete. It's also discrete. Not so many continuous parameters. Maybe we can use the E-graph technique for some discrete additive manufacturing. Make it simple. We can start from
very
that.
detailed.
Yeah. Okay.
Yeah. And Peng Song also have a question, and I encourage him to ask you directly. So please.
Okay.
Hey, hi, Haisen. Thanks
Yeah,
for
long time no see.
thanks for a nice talk. I have one question about this Geometry project. Okay, so for this furniture, right? So on the market, lots of them actually they have this joints, integral joints, right? So so if you buy some furniture from IKEA, so actually they already have the joints, right? So, when you bring the parts, you can assemble by yourself. So I just wondering whether this integral joints is possible to be incorporated in your Geometry project. I mean, when you fabricate the parts, it already have joints like some holes or exclusions.
Yeah. Indeed, we have considered we want to do this because for carpentry the joints is very complex. Even for this, we can generate some many complex joints to combine the two parts. But for now, we did not consider that. In our current work, we only consider very simple joints. Very simple joints. And another point I want to say is different joints will affect the stress, the physical performance, such as how many stress it can resist. Our current work is also did not consider this, but I believe our work is general enough, can take that such consideration into. It's just to add another objective. Our current objective is we have three objectives. It's all fabrication related. Fabrication time, material cost, and the precision. In our paper, we have shown one example to evaluate the physical performance, how many stress it can resist. We have one single demo to show that. I think because it's related to the joints, different joints will have different stress performance.
Exactly.
Yeah.
I think that can be an interesting future work. I mean,
yeah.
How to fabricate the furniture parts with joints more efficiently.
Yeah. It's also how to fabricate exactly. Such very complex joints.
Yeah, it's not easy.
It's very interesting. Our current part is pretty simple. Yeah.
Okay.
It's kind of our current carpentry is do the rough machining, or is do a rough part. We did not consider to make each part have more detail, more geometry detail. Yeah.
Okay.
We can go further. Yeah.
Okay. Thank you.
Yeah. Thank you.
Yeah, and even if you consider joints in the loop, and also this processing time, assembly complexity and assembly time will also be highly affected.
Yeah.
But it's really like your workflow, like this kind of rough machining and fine machining. It's like these two stages.
Yeah, rough machining and fine machining.
Yeah, very interesting. And if you further consider hybrid manufacturing, I wonder whether this carpentry can be further extended to more general materials, or more general like the applications. Because for carpentry, you only need to consider this so-called subtractive manufacturing. You only need to do this cutting and assembly. But maybe for more general materials, you can consider more. You can evolve this hybrid manufacturing methods in the design, like metal, like plastic, like some other or some soft materials in the loop. It also implies many interesting directions.
Yeah. We can. Oh, it's really a good idea to combine this my first topic and the third topic. We have considered to involve 3D printing to the carpentry. It's kind of for a chair, for wood chair. We can printing on the wood. It's will ask us to do the optimization. When do we do the cut? When do we do the 3D printing? Maybe we can generate some new art, some new product combine the wood and the plastic material. Yeah, it's crazy.
Yeah. And I really think your two very good talks have some relevance, have some really high relevance inside. Yeah. Okay, so Peng Song, do you have further comments or questions?
Okay,
if no, okay.
Yeah, I have one last question. Okay, so I just want to ask Haisen. So you mentioned about this hybrid fabrication, right? So it combine additive manufacturing and subtract manufacturing. I just wondering, is this commercially available or is it still under research?
Yeah, it's available. Then you can see many such kind of machine, but it's mainly for metal, for metal material. It's not common for plastic. It's not always fabrication with plastic, just as common FDM machine.
Okay,
it's always use some metal powder. Okay,
so for the additive manufacturing and the subtractive manufacturing, do they use the same material, the same metal material, or different materials?
Commonly they use metal. They use same. They first use 3D printing, so 3D additive manufacturing to generate a 3D shape.
Yeah.
Then do the machining, do the fine machining over the surface, over the rough surface. Because there are many such kind of machines.
Yeah, I knew. I mean, for this currently, so for this metal 3D printing, right? So I mean, they can do this 3D printing, but the surface quality is not good. So that's why they use CNC machining to do the polishing.
Yeah. I also noticed that in our domain, there are many work focused on the plastic FDM method, but for the metal, I did not see any paper in graphics domain work on it. Metal related fabrication.
I know. I mean, they have this technique. Okay, I just wondering, when they do the fabrication, do the machine do it together? I mean, for example, one part is by additive, another part by subtractive, or is do independently? I know that. I mean,
it's additive. It's additive. First, use 3D printing method to generate a part, but the part have some layer staircase. For first staircase, we can use the machining, use a cutter.
Okay.
To carve over the surface.
Okay.
To make it very smooth.
Okay, I see. Okay, so I mean, yeah, that's reasonable. I mean, let's combine the complementary strengths of the two techniques.
Yeah. I have also considered other hybrid, such as 3D printing and molding.
Okay.
3D printing and molding, we can also consider to hybrid.
Yeah, exactly. Okay, that's also been interesting in this research topic.
Yeah. Thank you.
Okay, thank you, Haisen.
Yeah.
Okay, Professor Neil, do I have further questions?
No, I don't have further questions. And I have extra comments. And as you mentioned, this additive and subtractive are independent. They do not interfere, but they perform interleavingly on the same part. Yeah, so they are independent to each other.
Yeah.
Very, very cool. Okay, so Haisen, do you have any questions to the first talk? If no,
you have asked what I want to ask. I also want to ask Peng. Have you how challenge if you want to fabricate your design?
Okay, so I mean, if you use 3D printing, then there is no challenge. I mean,
No challenge.
okay, because okay, so the properties, I mean, the although it looks complex, right? But for 3D printing, especially we can use this 3D printing with water soluble material. So I mean, no, we don't need to care about the spot because it's water soluble. We just put in water and the spot will go away. So there's no challenge to do the fabrication in terms of 3D printing. And because it's small, so 3D printing is okay. It's only take maybe 10 or 12 hours to fabricate a puzzle. So it's not a big issue.
Yeah, I have another comment. It's not a research. It's not a research problem. It's just you have to. I know you have to do this topic for many years. Have you considered to do some commercial applications to have a company to have to have common users can.
Okay. Okay. At this moment, I will focus on research. Maybe later, maybe a few years later, maybe I can consider this. But at this moment, I mean, the focus is it's for research.
Okay.
And actually, I actually for some of this project, I released the code. So that means anyone can use the tool to design their puzzles.
Yeah, it's really cool.
Yeah.
Okay. Thank you. It's really good for the community and such that more people can be involved in this very interesting topic. It really, I think we still have many further projects to follow up. This related to this puzzle direction.
Exactly. Actually, I encourage students and researchers to study these problems. Actually, it's quite interesting. Yeah.
Yes, exactly. And also, you have this very neat formulation, geometry formulation, and also you have the very real objects and really
okay. So the puzzles, although so this looks quite a very small market, right? But the good thing of design puzzles is that you don't need to care about the physics. I mean, you only can only focus on the geometry.
Oh.
Exactly. Yes.
Yeah, that's the good thing of doing research.
Yeah.
Exactly. Yes. Yeah. Very good. Okay. So since we have discussed a lot, and I would like to conclude this session, and thank you again for this very nice talks. And thank you for all the audience if you are still watching our live stream. And okay, so that's all for today's session. Thank you.
Okay, thank you, Nili, and thank you, Haisen.